Welcome. So today we're continuing the fundamental theorem of calculus, looking at the theorem and doing some examples. We learned it before. The fundamental theorem before said the integral was the antiderivative evaluated at the endpoints. What we're going to do today is kind of the same thing, but we're going to do the derivative of the integral kind of in the opposite order. So what we're saying is suppose f is a continuous function, then the derivative of the integral is the function. Instead of the integral of the whatever is the, it's just a different order of things. This says whatever our function here, this is the antiderivative. I'm going to take the derivative of it to get the function. Notice the letters. There is a little bit of thought in this. If I'm taking the derivative with respect to x is our variable, and it's up here. A is just along for the ride. It's a constant, so it doesn't affect things. Because what is this inside? It's going to be capital F of x minus capital F of a. And then I take the derivative. I'm going to get f prime at x minus, now the derivative of this is a constant, is going to be 0. And then that is the derivative. So this is the same theorem. It's just written differently. So another way you can think of it too is, suppose the area is the integral from a to x of f of t dt. The derivative of a to x is f of x. And also, it's important to realize, if you have an x out here, don't put an x inside. It gets confusing. If an endpoint is x, the thing that's going along in the middle has to be something else. Anyway, let's take a look at these. What we're saying is the derivative of this is the original function. So do these two. Try these two out. See if you can get them. Okay, this first one, hopefully you can tell, the derivative from 1 to x, where x is a variable, of who cares what, dt, is going to be, well, that's our function. That's our f of x, or f of t in this case. So the derivative is just that of x. It's that simple. When the x is up here, we're taking the derivative with respect to x, and that's a constant. We just put x in for a variable. That's how easy this is. Now, this one's going to be a little trickier because, well, they're switched. The theorem said if x is up here, and it's not. It's down there. But hopefully you remember, I'll just rewrite this. If we have these switched, we can use a rule which puts a minus sign there. And then this, the derivative, is just like that. And there's a minus sign involved. So this is going to be minus x to the fifth 1 plus 1 over x quantity cubed. Now, it should also be noted, this one you could actually have multiplied it out, done the anti-differentiation, plugged the values in, and taken the derivative. But that's a lot of work, and this is a lot less work. Let's try one more, and we'll do this kind of together. So this one's trickier. The x is in the right spot here. It's on the top where we want it, but it's not x. It's 5x squared. X is our variable. 5x squared is not our variable, so this is tricky. This is going to be, let's say, well, let's work it out. It's, if little f of t is e to the t minus t squared, then the antiderivative, well, we don't really need to know what it is, but whatever it is, it's the antiderivative there. So this, we want d dx of the antiderivative at 5x squared minus the antiderivative at 0. That's what this is. Now, I want to take the derivative. Well, the derivative of the first one, this is a function at 5x squared minus, well, constant. This is a chain. Outside function, inside function. So in order to find its derivative, we take the outside function at the inside, the derivative of the outside at the inside times, not composable, but times, the derivative of the inside. Now over here, capital F of 0 is a number. The derivative of a number is 0. That may not look good yet, but this, the derivative of the antiderivative, is the original function. So it's little f of 5x squared times 10x. So I'm going to rewrite this, the 10x in front, just because it's easier. Now, I want the function at 5x squared. This is the function at t. If I put 5x squared in for t, I get e to the 5x squared minus 5x squared squared. That's going to be 25x to the fourth right there. But right now I don't want to multiply it out and write it out. That's just another extra step for something that's not going to be particularly useful. This is how you do it. This one is definitely trickier. If the first one made sense, if the second one, after a fashion, made sense, and you're kind of struggling on this one, you're probably doing right. Eventually, you should look at this one and go, I can do that one too. But right now, just take some time. Until next time, this is Dr. Jeff.